Hi and welcome back. So in this problem we're going to do pretty much the exact same thing that we did in the last problem, but just with a little bit of a twist. It's actually going to be a little bit different. So in this problem we're going to take the following function. X of t is equal to 2 sine of 12t minus pi over 4. And we are going to take this and we are going to represent this as a sum of complex exponentials. Let me just make sure that I wrote that down right. 12t minus pi over 4. Yeah. 12t minus pi over 4. Pi over 4. So we are going to take this expression and represent that as a sum of complex exponentials. So if you want to pause the video, now's a great time. And now I'm going to just start working through the problem. So if you remember in the last video when I said that when we got the formula for dealing with a cosine, to getting a cosine down to a certain form as a sum of complex exponentials, we did that with a cosine. We didn't necessarily do it with a sine. So there are a couple of different ways we could tackle this. The first way we could tackle this is by just applying a phase shift to the sine just from the outset, more or less. We could, and I forget exactly what the phase shift is for a sine off the top of my head, so that might be a clue to say we're not going to do it exactly that way. We're going to do it a different way. Or we could figure out the same way we figured out what the cosine representation was in terms of the sum of complex exponentials. We could do the same exact thing for the sine. So let's go ahead and I'm going to write down Euler's formula again, which was e to the j theta was equal to the cosine theta plus j sine of theta. And if you remember what we did in problem number 19, when I first figured out what the representation for cosine was as a sum of complex exponentials, what I did after that was I just wrote down the complex conjugate of this expression. So if I take the complex conjugate of both sides, I get e to the minus j phase is equal to the cosine of theta minus j times the sine of theta. And so now if you remember what we did in problem 19, we added these together. So now, instead of adding them together, because in that video I wanted the sines to cancel out, I'm going to subtract them here. Because now if I subtract them, the cosines are going to cancel out. So if I subtract here, I get e to the j theta minus e to the minus j theta is equal to cosine theta minus cosine theta. That cancels out. And then I have j sine theta minus negative j sine theta. So I'm left with 2j sine theta on this side. And so now what I can do is I can go ahead and divide both sides by 2j. So I am left with 1 over 2j e to the j theta minus 1 over 2j e to the minus j theta. That is going to give me my sine theta. So now the last thing I can do is say, what if I had an amplitude in front of that sine theta? What if I had some amplitude k there? Well, I just multiplied that sine theta by k, so I have to multiply everything on the left hand by k. So I have k over 2j, k over 2j. And this is the expression I'm going to use. K over 2j e to the j theta minus k over 2j e to the minus j theta is equal to k times sine of theta. So now, the very last thing I'm going to do to get this into a super general form is I'm just going to replace that theta with omega t plus phi. So now I've got my general sine function here, the most general sine function I can have. And that gives me k times the sine of omega t plus phi, is going to be equal to k over 2j. Anywhere I see a theta, I'm just going to replace it with omega t plus phi. K over 2j e j e to the j omega t plus phi minus k over 2j e to the minus j omega t plus phi. And now, just like I did in the last video, I'm actually going to skip a step instead of writing this all the way out. Or actually, no, I'm not going to skip a step. I'm just going to do the whole thing, write the whole thing out. So hopefully you can follow this. We have k over 2j. I'm going to multiply the j into these expressions. So I've got e to the j omega t plus j phase, that's my exponent, minus k over 2j e to the minus j omega t minus j phase. And now the last thing I'm going to do is because I'm adding exponents here, is I'm just going to rewrite that as k over 2j e to the j omega t e to the j phase minus k over 2j e to the minus j omega t e to the minus j phase. And now I'm just going to go ahead and switch the order here. Equals k over 2j e to the j phase e to the j omega t minus k over 2j e to the minus j phase e to the minus j omega t. So now I've got something that looks a lot like what we did in problem 19 when we did this with cosines, except now I've got a 2j here. Instead of dividing by 2, I've got 2j. So one of the things I can do here, and this is the point where it's important to remember that j is equal to the square root of -1. That's our kind of you can think about it as like our imaginary unit vector, almost, on the real imaginary axes. And I'm going to, right now, pretty much, well, let me ask you this. This is kind of it's a fundamental property of the imaginary unit number, the imaginary unit, that if I take 1 over j times j over j, on the bottom I'll get j squared. And remember, if I square this, that just gives me -1, right? So I'll be left with j times 1 is just j, divided by -1, which is equal to -j, right? So now if I put that into this expression, I get that I have, on this side, I have minus j, and actually here, I'm going to write it this way. K over 2, and I'm dividing that by j, and that's the same thing as minus j, e to the j phase, e to the j omega t, minus, and let me actually write, here, I'll write it like this, minus k over 2 times minus j, except I'm going to go ahead and take out the minus sign here. I'm going to write this as just positive j, and put the minus sign in here, plus k over 2 times j, e to the minus j phase, e to the j omega t. Give myself a bit more room. And now what I'm going to do is remember what happens when, let me ask you this, remember our real and imaginary axes. So I've got a minus j here, but let me ask you this, is this minus j that I've got drawn right here, is this in polar form or is it in rectangular form? Hopefully you can see it's in rectangular form, right? It's telling me to go down 1 unit in the j direction. It doesn't tell me anything about what the angle is. It's just telling me go down 1 unit in the j direction. What would it look like if I wanted to represent this in polar form instead of in rectangular form? Well, the angle I rotate through from the positive real axes. The angle would be minus pi over 2, right? I'd rotate through that axis, and my magnitude would just be 1. So I could represent that as k over 2 e, there's a 1 in front of that e, but it's k over 2 times 1 e to the minus j pi over 2, and then I've got all this other stuff, e to the j phi, e to the j omega t. And then I've got k over 2 again, k over 2. And again, look, I've got a j here. And again, let me ask the same question. Is this j in polar form or is it in rectangular form? And hopefully you can see again, this is also in rectangular form. This is telling me go up 1 unit in the j direction. Go up 1 unit in the imaginary direction. It doesn't tell me what the angle is explicitly here. So if I want to write this in polar form, my angle from the positive real axes is going to be positive pi over 2, and my magnitude is going to be 1. So again, I have k over 2, magnitude 1, e to the positive j, pi over 2, e to the minus j phase, e to the j omega t. And now the very last thing I'm going to do, and this might actually have to be, I know I'm running long on this video, and I'm running out of digital paper too. So the next thing I'm going to do is I'm just going to, the same way that we broke up these terms up here in my exponential by being able to multiply two different exponentials, I'm going to combine these two terms right here. And the same thing for these two terms. And I'm going to get that this is equal to k over 2 e. How do I want to do this? I'm going to say, I'm going to say that this is equal to, I'm going to factor out a j. So I have got j minus pi by 2 minus pi by 2 plus my phase. And I'm just going to go ahead and switch the order around. I'm going to say I've got phase minus pi over 2 e to the j omega t plus k over 2, and now I'm going to do the same thing over here, factor out a j, e, or else, actually no, I'm going to factor out a minus j here because I want this to be my complex conjugate over here. So I'm going to factor out a minus j, and I'm going to get the same exact thing when I factor out a minus j, right? I'm going to get minus pi over 2 plus phi. And now I'm just going to switch the order. I'm going to get phi minus pi over 2 times e to the j omega t. And now I've got a formula for representing a sine function that is going to work perfectly. Remember that this is all equal to k sine omega t plus phi. Let me write that down here. This is all, choose a good color. That's a good color. This is all equal to k sine omega t plus phi. So now that's pretty much what we were given in this problem. We were given that, let me write down the problem again. We were given 2 sine of 12t minus pi over 4. This is what we were given. So now we've got a great formula for writing down what this is in terms of the sum of complex exponentials. So we have 2 over 2. The 2's would cancel out because our k is 2. So we just have 1. E raised to the j times phi minus pi over 2. So our phi is minus pi over 4 minus pi over 2. So if I have negative pi over 4 and I subtract out another pi over 2, I'm left with minus 3 pi over 4, because my phi here is minus pi over 4, and I subtract out another pi over 2. Then I have e to the j omega t. My omega is 12, so e to the j 12t, plus k over 2. My k is 2, so 2 divided by 2 is 1. E to the minus j phi minus pi over 2. So I have minus j, and phi minus pi over 2, we already figured out it is minus 3 pi over 4. So I have minus, I could put in minus 3 pi over 4 here, but I'm just going to go ahead and let those minus signs cancel out. So I have e to the j 3 pi over 4. Or else, actually, no, you know what? I'm going to leave the minus signs in so I can really clearly see the complex conjugate here. E to the minus j times e to the minus j 3 pi e to the minus j times e to the minus e to the minus. Sorry, I'm getting confused here. E to the minus j negative 3 pi over 4, and then I just have to multiply that by e to the j. And sorry, that should have been. Oh, I made a mistake up here. This should have been e to the minus j omega t. So I have e to the minus j 12t. Sorry, I made that mistake down here, and I didn't catch it till I made the mistake up here. Didn't catch it till down here. So anyway, that is pretty much it. We figured out what our sine function was in terms of a sum of complex exponentials. So hopefully you found that useful. I know it was long, and I know that I made a mistake in here. If you're going to write down this formula, write down this version. So hopefully you're watching this all the way to the end of the video. Anyway, thanks so much for watching, and I guess I'll see you in a future video.